to input-output devices, controlled access to files, system access, error detection and response, as well as accounting. We will also briefly go into reviewing what we had already covered in terms of the objectives of an operating system in regard to convenience, efficiency, and ability to evolve. Then we will look at the kernel, which we already looked at, but now in more detail. So everything we are doing today, we are just going deeper into details of the kernel, the evolution of an operating system, how operating systems started, and how they have come about. So we'll be looking at the upgrades to hardware and the new types of hardwares which have made it possible for operating systems to work the way they do work. We will look at serial processing like it was then, batch processing, unit programming, and then what we currently run on, which is multi-programming. Then we will go into processes just to understand processes and how they normally work. Then after that, we will look at memory management. We'll also look at virtual systems. We'll also look at file systems, paging, information protection and security, access control, information flow control, certification, as well as scheduling and resource management in operating systems. And here we will be looking in terms of fairness, in terms of if it is a program, how is it supposed to be served fairly by the operating system, differential responsiveness, efficiency, and we also look at the major elements of an operating system. We will also look at the system structure, then the operating system design by use of examples of the common operating systems which are in use in modern days. And here we will basically look at the Windows operating system compared to the Linux operating systems. So these are the two operating systems which most definitely as a student of computer science or as a student of IT, you will definitely come across. So that is what we will use to do the comparisons. Then we will also look at the operating system design hierarchy as well as the characteristics of modern operating systems. So that is in a nutshell what we shall be doing. So let us just have a recap of what we were discussing last time, where we were looking at an operating system as a software that is able to provide or is able to control the operations or the execution of other programs in the computer. And we also said that it acts as an interface between applications and hardware. So that is basically what an operating system is. And with these two, you will find that it performs the function. Sorry, let me do that. With these two, we said that it performs the functions which we were calling abstraction and arbitration. If you remember, there are these two functionalities we talked about. So the goal of any operating system will be either to provide abstraction, and if you remember, we said that abstraction works in the context of hardware. So when we are talking about hardware, we are basically looking at abstraction. When we are talking about providing services for the applications, then we are looking at arbitration. So that is basically what the operating system does. Then, in doing those two functions, it is trying to achieve these three objectives. One is to provide convenience. And when we are talking about convenience, is trying to make the computer more convenient to use or more attractive to work with. That is why we provide things like the graphical user interface. We provide things like the graphical user interface. We also provide memory abstraction, like we will see. and many other services which are trying to make the computer more convenient to use for the user. So a user doesn't need to remember what are the commands, how are they written, because that can be understood by a programmer or somebody with experience with computers. But when we provide the user interface, whereby there are pictures and icons, then it becomes very easy for any kind of user to be able to work with an operating system. So that is what we mean by convenience. Then we are also looking at another objective, which is efficiency. When we are talking about efficiency, we are talking about now being able to use the minimum resources and provide maximum output. So we want to get as much output as possible from the minimum resources used. So here is where we are looking at proper usage of memory. And when we are looking at this memory, we are basically looking at RAM. We're also looking at proper usage of the processor. And that is why when we shall be looking at the evolution of operating systems, we will be looking at the concepts which started with serial processing and batch processing and uniprogramming as well as multiprogramming. Why did we move towards multiprogramming? It is so that we can efficiently or make sure that we are maximizing on the usage of the processor. We're also looking at maximizing on the usage or proper usage of the input-output devices. And here we are looking at this in terms of plug and play. You know, what we normally talk about is plug and play. So whenever you bring in a new hardware component to your computer, you do not need to program how it will be working, what it will be using. You just plug it in and the operating system is able to configure that hardware component to the proper usage in the computer. Then we are also looking at the ability to evolve, whereby we are trying to permit effective development, testing, and introduction of new system functions without interfering with the service. Just like we were talking about plug and play for the hardware, here we are looking about the new software which comes in or improvement of the current operating system. So we are looking at the improvement of the current operating system, whereby you can update it, and when you update it, you are making it more efficient, more useful. We're also looking at new application programs, as well as utility programs. So all of these, what we are saying is that you can introduce them, you can make the operating system become better, but you are not affecting its service. The way it used to provide the services to the user, it continues to do that even in a better way as it evolves. When we are talking about evolving, we are talking about evolution from when it was just a simple thing to when it can be able to work even better. And that we can find with the current operating systems we use, like Windows, even Android, which we find in our mobile phones. Many of them, they are running on Android operating system, and that is a Linux-based operating system, and it keeps on being improved in terms of the functionalities it can have, the security features, and so on. So all of those are being provided for and still ensure that the operating system doesn't degrade in terms of service delivery. Then, when we are looking at a computer, we look at it this way, whereby at the top, we have the end user. And the end user will always interact with the application programs. Here, think of the Microsoft Word, the PowerPoint, think of a browser like Chrome and so many other application programs. Those are the ones which the user interacts with. But right below them, there are the utility programs, the ones we were saying that you will find them being worked on by a programmer. Program development programs like C, C++, Java, those are the ones we are calling them utilities. Even the antivirus software is a utility. Those ones help us in creating new programs or protecting our systems from interference or from viruses. So that is why we call them utilities. And right below them, so these two, the user can interact with them in the normal English language. But for them to interact with the computer hardware, because it is the computer hardware which does the actual execution. And when we are talking about the computer hardware, think about the processor, think about the random access memory, think about the registers as we talked about them, and the cache memory, and the external storage, the keyboard, the mouse. All of those are computer hardwares. These ones understand the machine language, or the language of zeros and ones. So it is the work of the operating system to translate these English readable words or instructions into the computer instructions, which are in machine language for the computer to be able to understand what to do. It executes and then gives back the response. And that response is translated back by the operating system. So that we already mentioned. And those are the layers of an operating system. So if somebody asked you in an exam, what are the layers in a view of a computer system, then you can give that. So when we are looking at the services provided by an operating system, we look at them in terms of the functionalities you find within a computer system. So within a computer system, you can be able to develop programs, like we have said, by use of applications such as C, C++, Java, Python, Ruby, and many others, etc. So all of these are able to be able to create new programs. And we normally use them when we are working with editors and debuggers. And for them to be able to work, we normally use what? In order for them to work, there are things we call compilers. And what is the name of the other one? I want to ask and see if we are together with everyone. We have compilers and the ones which now translate or help in execution. Daniel, what do we normally use? A compiler or a what?
Translator.
A translator. Thank you, Aldo. So those are the ones you will find here when we are talking about program development. So as much as we are using these programs to develop other programs, then we can use editors. And once the editor, when you are finished working with an editor, you will either need to compile the program or to translate it so that it is executable. So that is what we mean by program development. Another service is program execution. So when you are doing program development and execution, you will need the operating system. So for any program to execute, it will need to execute on top of an operating system. So for example, if today you have been given a new laptop or a new desktop computer, the hardware, and you want to install Microsoft Word, or you want to install any other program, there is no way you will install it directly to the hardware without having an operating system. The first thing you will need is to install an operating system, either Windows or Linux or Ubuntu, whichever. And once you have installed that operating system, then it is at that point you can now run or execute other programs. Then we also provide, an operating system will provide the service of accessing input and output devices. until you have installed the operating system. That is when now you can start configuring the other hardware, which we are calling the input and output devices, be it a keyboard, be it a mouse, be it a printer, talk of cameras, the sound producers, maybe a microphone or a speaker. All of these hardware components, they are going to be configured by the operating system for them to work together with the processor. So that is why the operating system is the one which provides access to these input-output devices. Then we also have controlled access to files, and here we talk about things like user levels. And when we are looking at user levels, we are looking at users who can read and write files, and there are those who can only read. So there are these several kinds of users. There are those who can read and write files, meaning that they can access it and they can make changes to it when we are talking about read and write. But there are others who can only read, or they can just view the files. And there are others who cannot even view the files depending on their access levels. So when we are talking about controlled access to files, that is what we are talking about here. There are those who have the rights, so they can be administrators. There are those who are just basic users, and that is being provided for by an operating system. When we are looking at system access, we are looking at things to do with authentication, and verification. So what exactly does this mean? When we are talking about authentication, we are talking about things to do with use of usernames and passwords. So that is basically what we mean, that the operating system is the one which manages how people are going to access to this system. And when they are giving you authentication and verification, they are basically trying to check, or the operating system is basically trying to ensure that you are the user who is supposed to access that system. So when you provide your username and password, since your account had been created, like if it is an administrator, they will have their username and the access level is defined, and then the password which they can log in with. So when we are looking at system access, that is the aspect we are looking at in terms of the use of usernames and passwords to authenticate or to verify users as they log in into the system. So that is another service. Then another service provided by the operating system is error detection and response. So when we are looking at error detection and response, we are basically talking of if there was a virus attack, or there was a file which had been maybe maliciously or erroneously deleted, then it is the work of the operating system to detect that, especially during startup. The operating system does something we call this error checking starts with during startup. There are two basic processes which normally take place. One of them is what we call the POST, or the power on self-test. This is one of the activities which takes place. And when it is happening here, it is just the hardware which is being checked. Check the keyboard, check the mouse, the processor, the memory, to see that they are all okay, because they depend on power. Just like we normally say, the bloodline of any computer is electricity. So they all depend on power. Those signals are transmitted by use of power, electricity or electric current. So that is why it is very important to first of all perform a power on self-test. This one checks now all the hardware if they are okay. Then after that, there is another function which takes place. We normally call it the BIOS test. This is the basic input, output, system test. What we are calling the BIOS. So here, when we are performing the BIOS, basically it is the system trying to check if the software components are fine. So check the operating system. Is there any missing file? Is there any error to the to the memory area where the operating system is stored? Is there any kind of corruption which has happened to the operating system files? Because at this time, when you are doing the BIOS test, the control is within the kernel. So that is something you need to note. When we were talking about the kernel in the previous class, we said it is the core of the operating system. So every activity is taking place in the kernel until that the kernel is sure all these other files are okay, then the control is transferred to the entire operating system and its location where it is. So that is what happens. So here we are checking any memory error, device failure, software errors like arithmetic overflow, access to forbidden memory locations. All of these, they are being performed by the operating system during startup. Then during the normal operation, the operating system will be able to grant request or deny request to applications depending on the user levels. So depending on what kind of the user has logged in into the system or has been loaded by the operating system, it is able to either grant access or deny access to some specific applications or system areas. So that is what happens. So at any time, if there was an error, let's say during the power on self-tests, there are normally noises. Ile siku utasoma there is a unit called hardware support and maintenance. Kuna unit ingine inaitangwa system administration. That is where you learn some of these things. You will hear some beeping noises when you are booting up your computer, or there are messages which are brought to the screen which are able to tell you that everything is okay or something is not okay. So during power on self-test, those computers of before, they used to make some noises. If you hear a continued noise, it doesn't stop. It means there is a problem. If the BIOS is booting and there is an error, it will also give a beeping noise. And those noises had some explanation or had some meaning. So if you see this kind of a beep, you will know maybe that is a keyboard error. You hear this kind of a beep, you will know that is a processor having a challenge and so on. So it is the work of the operating system to be able to notify the user. If it is able to correct, it will correct itself. If it is not able, it will give you the user a message so that you know what to do with it. And then after that, you can correct the problem and then booting process continues. If there is any challenge, you will see that during the operation of the computer, it will tell you this memory location is not accessible. There will always be some pop-up message or some kind of dialogue coming to your screen telling you that you're trying to access a memory area that is not accessible. You're trying to delete a file that cannot be deleted, access denied. Such messages are provided by the operating system. Then we continue to the accounting service. The operating system is able to collect statistics, monitor performance, used to anticipate future enhancements, and used for billing users. This is something you find commonly if you tried to do the Control Alt Delete. That is a service. Let me just try it for you. So if I did, let me just do it, Control Alt Delete. If I press Control Alt Delete, I will be able to open the Task Manager. And the Task Manager is a component of the operating system, or is a service provided by the operating system, which is able, let me see if you can see it, the Task Manager, and see what we are talking about. So are you able to see the Task Manager?
Yes, we are able to see.
Okay, so when you are looking at the Task Manager,
Ah, we are not.
you are able to see the applications that are running. Kindly mute your mic. Okay, thank you. You're able to see the services that are executing. You're able to see the programs that are running. You're able to see the background processes. You're able to see how the CPU is being utilized. Maybe now I'm utilizing up to 37% of my CPU. The memory, that is the RAM, is being utilized up to 81%. The disk is being utilized 3% of it. The network is at 1%. And you see, all of that you are able to tell. You can even tell the application which is using the most power. Like here, we're looking at power usage. Chrome, the Chrome application is using very high power because of maybe the pages that are open, and maybe this meeting that we are running here is able to consume a lot of power for it to work, because all these applications, the computer itself, they depend on power. So the task manager is able to tell us that. It is also able to give us the performance of the CPU. So during the operation of this machine, I am able to see the usage of the CPU, the memory, the disk, the Ethernet, how it is running, the number of kilobits I'm using at any one given point for this service to be able to run. All of that is provided by the task manager, which is a component of the operating system. Even app history, even during startup, which applications are normally starting and how they normally run. Users who are available in the system, at this time it is only me as the user, and then the details of the services which are running are normally given there. So that is one of the tools which are used by the operating system to be able to provide statistics of how the system is running. So I hope up to there something has made sense. So when we are talking about the operating system providing statistics or giving an account. So when we are talking about collecting statistics, monitoring performance, used to anticipate future enhancements. If I can see that my memory is being used up a lot, I am able to think about acquiring a new memory stick, which will be able to enable me work. When you install, like those in the cybers, when you install those applications for billing, they are normally embedded within the task manager so that they can be able to bill users, maybe for the duration of time or for the resources they have consumed when they were logged in into the system. So that is how the accounting function is provided by the operating system. Then the operating system functions the same way as an ordinary computer software. It is a program that would normally need to be executed, and its execution begins at startup. So when we are talking about this execution, we are saying that it starts at startup with power on self-test, then BIOS is loaded, and then control is handed to the operating system entirely. So that is how the program is normally executed, or how the operating system is normally executed. The execution begins at the startup when you are doing power on self-test. Then BIOS is loaded. After loading the BIOS, control is added over to the operating system. Then we are also saying that the operating system will relinquish control of the processor to execute other programs. Like we will see, it is the operating system which does scheduling of how processes are going to be entering the processor and execution takes place. So maybe in the next class, we shall be discussing that. After the next class is when we shall now start the practicals and trying to see how these things operate. Then, when we are looking at the computer system and its services, or the operating system being a resource manager, so it is going to manage the memory, whereby the operating system is going to be given a part of the memory. And here, when we are talking about the memory, we are referring to the RAM. So when you look at your computer, when you go to your task manager, or you go to your C drive and you start looking at the resources, you will notice that your operating system will take up some part of the memory or the RAM. If you have like 4 GB of RAM, let me just see if I can be able to show you that. Even if you have 4 GB of RAM, you will not be able to use the whole of it. Why? Because some part of it has been given to the operating system automatically. Like it is the operating system which, if you have 4 GB, you will notice that like maybe 200 MB or 400 MB is being used up by the operating system, and that remains like that. There is nothing much you can do. Then after that, the operating system will now give or allocate other users that the rest of the memory according to the way it wishes or according to the need. So I'm trying to look at the properties and see if I can be able to show you that. Now let me see if it is able to open. So like for instance, when I go and right click on my computer, I am able to open this. Let me try and see if I am able to share this. Guys, I don't know, are you able to see the system properties which I'm showing there? If you look at these system properties, this computer has like 4 GB of RAM. But the 4 GB, it is only 3.9 GB, which is usable. So it means like a small percentage has been given to the operating system so that it is able to work from there. That is what I wanted to show you guys, that if you have a certain size of RAM, it is not going to be used entirely, or it is not usable in its entirety, but some of it will be given to the operating system. I hope that is clear. Let me just go back to the presentation. So that is what we are trying to show here. This memory or the RAM, some bit of it will be given to the operating system. And then the rest is what is usable, whereby programs and data, as well as instructions, which are part of the programs, are going to be running from. Then, on the other hand, inside the computer, we also have the processor. The processor will also be managed by the operating system as well as the input-output controller. So these are parts of the registers. The I/O controllers are just part of registers which are normally managed by the operating system on behalf of the processor, so that you can be able to connect keyboards, mouse, printer, cameras, all of those, even these storages and other programs. Like if you are running a Linux-based operating system, it is very possible to run an Ubuntu operating system from a flash drive, which is external to your operating system, and you're able to do that without any challenge. That is something I will show you how it is normally done, because one of the practicals we will be carrying out is installation of an operating system from scratch. And it is not necessary that you will need to maybe uninstall your already installed operating system, but you can also run a virtual machine. And so I will be able to take you through the installation of a virtual machine. And then once you set up the virtual machine application, you can install another operating system within your operating system. And basically, I will be looking at us installing a Linux-based operating system, because it will help us to run some of the commands which normally show how systems are executing processes. So after the next lecture about processes, then we can start our practicals with the installation of an operating system and then running some of these functions like we are discussing them now. So let us continue and we look at the kernel. The kernel, we already said that it is the main part of an operating system, or the part that is always inside the main memory. We said that it contains the most frequently used functions, or the core of the operating system, whereby that cannot be found there. Like I was explaining in the previous class, it is that the kernel contains those functions. You can remove functions of the graphics, you can remove functions of the maybe media, let's say audio, video, all of those you can remove. And still the operating system is able to provide its services. But there are those core functions you cannot remove, like scheduling the processor or scheduling inside the processor, also execution of instructions, that is in terms of step-by-step functioning of the operating system, that cannot be removed. So the kernel contains that core of the operating system, which is found in the main memory. So let us look at the evolution of the operating system, and we are looking at it in terms of where it came from. So it started with the basic hardware, and there have been new types of hardware which have come in place. There have been improvements of the hardware in terms of the processor, the operating system itself, on the memory, and all of that. So that is where things have come from. And when operating systems came into existence, we started with serial processing, whereby it's like there was no operating system at all. Everything was manual. So machines used to run from a console, and there were display lights and toggle switches. And then there was the input device and the printer. So think about the history of computers. If you did this in one of your classes, you read about the history of computers, whereby we used to have memory drums and we used to have the punch cards. So those are the ones we are talking about. It was like the basic calculator, whereby somebody would come with your work, which you want to be computed, and then you will be feeding it in a sequential. That is why we call it serial, or what we can also refer to as sequential. And when we talk about something being sequential, is that it is one instruction after the other. That is what we mean. So setup included loading the compiler. So you have your compiler, your source program, and then the compiled program is run so that you can work on your data. So it used to be purely manual, whereby a user would come with their program, then load it into the processor, and then it would start executing instructions as they are being given by the user. So this one required people to be real programmers, where they need to know which instruction to give the processor so that it can perform that specific task. So that is where operating systems started, being manual and being sequential, or what we call serial processing. Then after that, we came to the batch processing systems. And when we talk about batch processing, is the concept whereby now systems were a bit improved, and since now programs could be loaded into the memory of the computer or the computing device, then, and it would be just one program after the other. So what happened is that you needed to have all the jobs. That is why it is called a batch. So you would prepare a batch of all the jobs which need to be processed by that a program which is in the processor at that one moment, and then it would execute all of them at once as a batch. So that the main idea was that you don't need to keep on loading a different program at any one given point. You can load one program, let's maybe it is performing calculations in Excel, for example. So all the jobs which are being executed in Excel will be processed as a batch or as a group, because it is the Excel program which has been loaded. So this is an example I'm basically giving. So once you are through with executing those jobs which are required Excel, you remove that program, then you load another program. Let's say now it is like maybe Word, all the text-based programs, then the applications, then they would also be executed. So the main concept here is that the main memory and the availability of execution was the main concept, whereby the monitor was the main memory which used to load the program and the instructions. Then after that, execution is done as a batch. It used to have the job control language, and the job control language was a special type of a programming language which provided instructions to the monitor or to the main memory on what compiler to use and what data to use for execution. So that is how batch processing used to work. So there we used to have the issue of memory protection, such that you do not allow the memory area containing the monitor to be altered, because now you needed the monitor or the one which is trying to execute the instructions having the program loaded. So if it is the Excel, the location where the Excel is running from, it needs to be protected. And then there used to be a timer, so that you ensure that it is not just this one program which is inside the system for all the duration of time, or it is monopolizing the system. So each program is given its own time, and after that time is over, it would be loaded from the system and another one loaded into the system. So that is how it used to work. Then we came into uniprogramming. Now with these concepts kept on changing because of advancement in the creation of computer systems and different hardware components becoming better and better. So here, when we come into uniprogramming, we are looking at the third generation of computers, whereby now we are looking at the processor waiting for the input-output instruction to complete before proceeding. So you would have this program which is loaded into the computer, and then since it is just one program, it would wait. So it is running at that time, then it keeps on waiting for the input-output instruction. Maybe it is the keyboard which needs to give an instruction so that the next execution can take place, and then it keeps on waiting. So uniprogramming had a lot of time wastage. And that is where now multi-programming came in, whereby you could have several programs loaded into memory. And here we are looking at the fourth generation of computers, or what we are calling the present day computers, although we have moved into the fifth generation as well. But most of the present day computers are still in the fourth generation, whereby you can have multiple programs being run in the main memory. Like now you can load maybe Word, Excel, you can load Google Chrome, you can load Facebook. All of those programs are in your main memory. And when they are in your main memory, as this one is being executed, or you have opened program A and you were running an activity which requires maybe you are trying to install a program. So as it is running, it comes to a point where it requires you to confirm something, or it requires you to click for it to continue. So as it is waiting, program B will start running, or will take over the processor so that it continues to run, so that you don't waste a lot of time as it is waiting for this one to complete. Because it may run, then it waits for something, you give it, then it runs, it continues to wait for something else before you give it, another program is running. So when you are combining program A and B, you see that time has been reduced. So this is multi-programming with two programs, A and B, running. You see that they are able to, what do we call it? They are able to exchange the processor so that the processor doesn't waste a lot of time waiting for the one program to complete, so that it is also working on the other one. So imagine having it with three programs. Then it means as the first one is waiting and the second one is waiting, the third one can run. So it goes on like that. That is why we have scenarios where you can run multiple programs. And that is why we talk of it being multi-programming. It is not that you are running those programs simultaneously, or they are being executed by the processor simultaneously. No, they are being put in the main memory simultaneously. Each one of them has been allocated some RAM space, and as it is executing in the processor, whenever it needs something, or whenever it is waiting for some input-output activity to take place, then the other one can take over the processor and execute. And with that, you reduce the time it is taking the processor to wait for one. And this is an example now of how the processor is being utilized. When you are looking at the uniprogramming diagram here, comparing it with multi-programming, uniprogramming will take like 30 minutes to complete 3 jobs. Whereas multi-programming will take 15 minutes to complete the same 3 jobs, looking at these two diagrams, whereby the CPU, which is the processor, is wasting a lot of time. But here, it wastes very little time when it is at 0, because most of the time it is almost at 100%, meaning most of the time within these 15 or 10 minutes, it is in full capacity utilization. So that is how uniprogramming differs from multi-programming in terms of usage of resources and time spent within the processor. Any question regarding that diagram? Or is the diagram clear when you look at it? Okay, if everybody is clear with the diagram, let us continue. And here we are trying to show. We have job 1, which we could say it is from program 1, job 2, program 2, job 3, program 3. This one requires 5 minutes, the first job. The second one requires 15 minutes. The third one requires 10 minutes. This one requires 50 kilobits of memory. This one 100 kilobits. This one 80 kilobits. This doesn't need the disk. This one doesn't need the disk, but job 3 requires the storage disk. This doesn't need the terminal. This requires the terminal. When we are talking about the terminal, think of it as the screen whereby you need to interact, or there is a, what do we call it? A dialog box. This one doesn't require. This doesn't require a printer. This doesn't require a printer. That one requires a printer. So when it comes to multi-programming, processor use will be at 22% during this time when these three programs are running. But in multi-programming, you can use 43% of the processor and it will take less time compared to this one, which takes more time. Memory usage will be at 30%. Memory usage here will be at 67%, meaning that multi-programming makes better usage of the resources, the hardware resources that we have within the computer. Because if you are using just 30% of, like, let's say the RAM, then if it is 30% of 4 GB, then where is the other one going? Or why are you wasting the other one? Because you paid for it, you need to use it. That is always the concept which is provided there. So with multi-programming, there is better usage of resources and less time is normally taken when you compare it with uni-programming. And then we have time-sharing systems, and this time-sharing system use the multi-programming concept to handle multiple interactive jobs, whereby the processor time is shared among multiple users. Like one user will be accessing this processor at this time, and another one will be accessing this processor at another time. And this is what is shown here, just looking at batch multi-programming and time sharing. And what we are showing here is that time sharing systems are able, when we are looking at their objective, with batch multi-programming, we are maximizing the processor use. But in time sharing, we are trying to minimize the response time. The source of directives to the operating system, this one uses the job control language, this one uses the command terminal. So it means that every command needs to be put so that the processor can execute. And those have been compared by this diagram, which I will leave you to look at it. And then if there will be any question, we can come and discuss it and try to understand it. So I will leave it at that. And then we look at the major achievements which have been made throughout the evolution of the operating system, from the time we started with serial processing, batch processing, coming down to uni-programming and multi-programming. We started breaking down programs into processes. Memory management became very efficient, such that you can have several programs in memory and they are not interfering with one another. That is what we said the other day. Also, information protection and security with the memory management aspect, then information is protected and more security is there. Then scheduling came about, whereby you can schedule how the processor, so operating system, modern operating systems are able to schedule how the processor is being accessed or how the processor is being utilized at any given time, so that it is not idle. And then the system structure has also improved. So throughout that evolution process, these things have been able to be achieved. Now, let us come down to what a process is, because we have already talked about a program. So normally a program, once it has been loaded into memory, it will be broken down into processes. And that is why we define a process as a program in execution, or an instance of the program which is running on a computer. So I hope that makes sense. Does that definition make sense? When we talk about a process being an instance of a program running on a computer, think of this example whereby we are talking of a Word. You have loaded the Microsoft Word, or you have loaded the Facebook application. When you have loaded the Facebook application, it's not like you are using all the functionalities or all the processes within that program. Maybe at one time you are just updating your status. So at that time, it is just that instance of updating status which is working inside the processor. I hope that makes sense. At another time, it is maybe the messaging part which is running in the processor when you are chatting with somebody. So that is why we break down the program into processes. So as much as you have loaded the entire program into memory, at any given time, you will be working with an instance of that program. Has that made sense? Or am I making sense with that? Fred, I don't know if I am together with anybody. Benson, Mawira, Ado.
Yes.
It makes
It
sense.
makes sense. Yeah, it is making
We're
sense.
together.
Good. Thank you.
Thank you.
Okay, mute your
Okay.
mic, then we continue. And we normally say that when the process is working, it is normally characterized by a single sequential thread of execution or a current state or an associated set of system resources which are being used at that time. Like we are talking of the instance whereby maybe you are messaging at that time, you are using some specific system resources. Like for example, you might require the messaging aspect, which is taking some memory, and at the same time, you need some kilobits or some access to the network for you to be able to send that message. So you need to be allocated those resources for that instance of the program to execute. That is what we are saying. Then we come to what are the difficulties now when you are looking at designing that system software. One is the challenge of improper synchronization. When you are designing any operating system, the aspect of synchronization is very important. What do we mean? Synchronization in this sense, you need to be able to schedule all the applications in terms of allocating them memory and allocating them time to access the processor. And then you need to ensure that the process waiting for an input-output device will receive the signal so that it doesn't keep on waiting for an entire time, but it will never get access. Then there is also the issue of failed mutual exclusion. When we talk about mutual exclusion, we refer to the aspect that each program or each process which is in execution needs to be exclusive, or it needs to have its own resources allocated to it. That is something we are going to look at just in a while. Such that you need to give it some memory, you need to assign it to a register somewhere. You remember when we were talking about the memory access register, memory buffer register, all of those, it needs to be accessed. It needs to be given an index or an ID so that you know this is process number 1, 2, 3. It is supposed to execute at this time specified. It is using this and this memory. It is also using 1, 2, 3 instructions. So sometimes if you fail to exclusively assign its own resources, then there is a problem of mutual exclusion, meaning that it can interfere with other resources or with other processes which are also running within the computer. Then there is also the challenge of non-determinate program operation, whereby a program needs only to depend on input to it, not relying on common memory areas. So it depends on where it has been allocated. And then the challenge of deadlocks, which we will look at when we are looking at memory management and the process access. So any process will consist of an executable program. And when we are talking about executable program, we are looking at the instructions associated with that process. Here we are talking about the associated instructions. So that is the executable program, meaning that it is going to go together with the instructions, then the data that is needed by the program. So if you are trying to type something, you need to be having the instructions which are able to send signals to the processor so that when you type maybe a specific sentence, it will appear on the screen, and then the associated data which is coming together with it. Then you also need the execution context of the program. Like we will see, programs have different execution contexts. There is that stage where the process is being loaded, the process is being ready, the process is in execution, the process has finished or is waiting for input, output, and then the process is being exited. So there are those different contexts of programs which we will be looking at. So these three things are very important when you are looking at the process. It needs to have the instructions, the data, and its context. Like we will see, the last class we talked about direct memory access, and we also talked about interrupts, meaning that a process during execution can be interrupted. When it has been interrupted, you need to show that program status, like where it was, at what stage, which memory resource it was using, and which instruction was running. That needs to be saved somewhere so that when it comes to resume, you can resume from there. So it is something we shall also look at. So this is what we are looking at. When we are looking at the process, we are talking about process which is in the main memory, and the first process, then we have process A and process B. So this is a process list whereby we have process I, J, and then we have process A and B. Then you have the context, the data, and the program, the associated code or instructions which are going to be working on it. Then we have process B, whereby it is also having a context, data, and the associated instructions. And all of these are going to be stored in a program counter. Like the next instruction is in a program counter somewhere. And then there are other registers we talked about, the memory address register, the memory buffer register, all of them with their functions there. So that is how a process is going to be implemented. So this could be like an entire program, but within that program, there are several processes. So how do we manage that memory, the main memory? We manage it through process isolation. This is one of the activities we shall be doing. And process isolation is trying to achieve what we have called the mutual exclusion. Mutual exclusion function. And then there is also automatic allocation and management, such that when we are talking about automatic allocation and management, automatically when you load a program, like when you are trying to open a new program or you're starting a new program, it will be automatically allocated a memory space. And then that space will be automatically managed. Then we also support for modular programming, meaning that the programs are going to be put in modules or in units. Like you are working with a particular unit, then that is the one which is working, like we have talked about. So modular programming is the use of the concept of processes. Like as much as this whole program has been loaded, it is just one specific module which is active at any one given point. Then protection and access control, meaning that you need to ensure that these programs are not interfering with one another. And then long-term storage is also very important to be managed, because all these programs are stored somewhere in a long-term storage. The data we are talking about is somewhere in a hard disk. So all of that needs to be managed. And then we have the concept of virtual memory. So at times you can use up all your RAM. When you use the whole of it, then programmers can address memory from a logical point of view. So when we are talking about a virtual memory, we are looking at memory that is not real. it is logical. Just like if, for example, I told you to touch maybe this PowerPoint presentation, you cannot touch it. We are looking at it from a logical point of view. So the same way, we can access a memory from a logical point of view, whereby we are trying to get some part of the main of the secondary memory, like from the hard disk, and reference or make reference to it. So we are saying at one time you can have a process which is running from the secondary memory, and if it is not frequently accessed, it will be put in virtual memory so that it appears like it is on the main memory, but in real sense, on the main memory, we have just put. So here we are saying that if, and this is an instance, so let me say instance, if A is large or not frequently accessed, it can be put into secondary memory and then referenced there. So it appears like it is on the main memory, but in real sense, on the main memory, we have just put a reference or an index or a pointer to the secondary memory where it is stored. So at any one given point when we want to access it, we will access the pointer or the index, and it takes us to the secondary memory where that program is stored. So that is what we mean by virtual memory. Memory that appears to be like main memory or like real memory, but it is not really the real memory. It is an index or a reference to another storage somewhere. And this happens if a program has a very large or it is consuming a lot of memory. And since we are working with an instance of it, then the rest of it can be stored somewhere else, and then we just access it as we need it from there. That is what is referred to as virtual memory. File systems normally implement the long-term and short-term memories, and information is stored in named objects which we call files. So when we come to filing, we have the concept of paging, whereby we are going to allow processes to be comprised of a number of fixed size blocks, which we call pages. So when we start working with processes, then these processes are going to be stored in memory in pages. And those pages are the ones which are going to be accessed by virtual addresses, because they are somewhere in a secondary storage. So we are going to create virtual addresses which are not real, so that they can always be referenced or they can be pointed to where they are. So each page may be located anywhere in main memory, but the real address or the physical address in main memory is the one which is stored in a page. And this is what we are talking about. So we can have A1 and A0, A2, A5. These are what we are calling a number of fixed size or fixed length frames equal to the size of a page. So inside the disk here, which is the hard disk, is where we have the actual storage, but inside the main memory, we have what we are calling the pages or the reference to those pages. So each one of these, like A9, it could be maybe pointing to the page we are calling 9, something of that sort. So this is how virtual memory addressing works, whereby the processor, like we said, it needs to access whatever it requires very quickly. So the virtual addresses are within main memory, which can be easily accessed by the processor. So the processor accesses the main memory very quickly, and it will always access the virtual address. But the real address is inside the main memory, and the disk address is also somewhere here. So the virtual address, which is inside the main memory, will be pointed into using the main memory management unit, and this one is where the registers are. So the registers will be storing the virtual addresses, and the real addresses will be found in secondary memory where you're trying to access. So the processor quickly accesses the memory management unit, which then invokes either the main memory or the disk memory or the secondary memory, and it can easily now reference there. So that is how virtual memory addressing works like. Then we also have the function of the operating system, which is about information protection and security, whereby there is access control. And here we are talking about regulating user access to the system. There is also information flow control, and we are talking about regulating the flow of information within the system and its delivery to users. Like, what a level do you have in order for you to access this information? Like, if, for example, you are logging into a website somewhere, and maybe there is the general information which is given on the site, and then there is some other specific information which require you to log in or to have some kind of login credentials for you to access them. And then we have the aspect of certification, whereby certification provides access and flow control to be performed according to specifications. Like whenever you are trying to install programs in your computer, programs are required to have digital certificates, so that those digital certificates can say this program is from an authenticated developer, or it is from this and this developer, and it is not harmful to the computer or to the operating system where it is being installed. So digital certificates normally serve those purposes. That is why sometimes when you are installing any kind of a program in Windows 10, it will be asking you that this program doesn't have maybe a certificate. Do we go on to install? Because it is looking for your authentication. Then there is the function of scheduling and resource management, where we are looking at the aspects of fairness. And when we are talking about fairness, it's all about giving equal and fair access to all processes. We are saying that you do not need to have a program or a process that is processor hungry, whereby whenever it gets into the processor, you can't really remove it from the processor, or it is always dependent on the processor. No, you need to be able to have the operating system that gives you fairness, making sure that all processes are able to access the processor and they are given fair and equal service. Then there is differential responsiveness, where we are talking about discriminating between different classes of jobs. Different classes of jobs have different access levels, or they need some kind of responsiveness. There are those which we talk about direct memory access. They do not need to go through the processor. There are those which we say that they have a very high priority, meaning that whenever they show up, whatever was being performed inside the processor will be stopped, so that they take over the processor, and once they finish, then they can be able to work. And then there is the aspect of efficiency, where we are maximizing throughput, we are minimizing response time, and we are accommodating as many users as possible. Then these are the elements of an operating system, whereby any operating system will always have the service call handler or an interrupt handler. There is the interrupt handler here, the service call handler, and then the short-term handler. Those are very important, whereby service call is from the processes, meaning that any time a process needs to access the processor, it is the operating system which has that element, or it is the operating system which will invoke that call, and that is found in the code. During the execution of a particular process, there can be an interrupt. Could be hardware, system, priority. Those ones we talked about. It is the operating system which should have that kind of an interrupt handler. Then it also has the short-term scheduler, meaning that you will pass the control to the processor or to the process so that it executes whatever it needs to execute and then brings back control to the operating system. Then there is the long-term queue, short-term queue, input-output queues. All of these are performed by the operating system. Then when we look at the system structure, it is the one we started with, whereby we are looking at it from different levels. And each level performs a related subset of functions, and each level relies on the next lower level to perform more primitive functions. Like from the higher level, we have the application programs. These application programs will require some more primitive functions which are provided by the operating system. And then the operating system will require more primitive functions which are performed by the hardware, like the processor. And that is why we are talking about decomposing a problem into a number of more manageable sub-problems. And here is the hierarchy we are talking about in the design of an operating system, whereby we are talking of, maybe an example is a shell, which is in level 13. This one, which we look at in terms of the user programming environment and statements in a shell language. We will practice this one when we shall be looking at the Linux operating system. When you create a shell, it's like you have created a kernel or a small operating system which has its set of instructions to be able to perform a number of tasks. Then from there you have the user processes, and these user processes are like operations like quit, kill, suspend, resume. These are commands you will find in the Linux operating system. We shall look at them. Then we have directories which are supposed now to create storages, and these ones you can create, destroy, attach, detach, search, list. All these are operations you can perform inside a directory. Then you have things to do with the devices. So here is the highest level or more critical level. And then we come down to file systems, communications, virtual memory, local secondary storage, and then primitive processes. You also have the others like interrupts, procedures, instruction sets, and electronic circuits. So these ones, we shall look at them when we will be doing the practicals and try to understand them. So when we will start the practicals, we will come back to this section of the lecture and start looking at those activities and the specific operations. So modern operating systems have the following characteristics. One of the characteristics is the microkernel architecture. When we are looking at the microkernel architecture, we are saying that there is that assignment of few essential functions to the kernel, and the kernel will be given address space. That is why some files you can never delete them, some files can never be stored somewhere in the C drive, in the process communication and basic scheduling. Then there is the characteristic of multi-threading, whereby a process is divided into several threads. So normally we shall start with a whole program. When we are looking at multi-threading, we can summarize it like as follows. It starts with the program. Then the program is broken down into processes. Then the processes are broken down into threads. So you start with the program, come down to processes, then come down to threads. And then we are talking about a thread being a dispatchable unit of work, whereby it can execute sequentially and it is interruptible. meaning that a thread will be executed, then the next one is executed, and the following one is executed. But at any one given time, they can be interrupted. So a process would be a collection of one or more threads. Then there is also the symmetric multiprocessing, whereby modern operating systems can have multiple processors. Like when we are talking about Core i3, Core 5, Core 7, Core 9, those are multiple processors within the same system, and those multiple processors are also being managed by the operating system, whereby they are going to share the main memory. They are also going to share the input-output facilities, like the keyboards, mouse, the printers, and all of that. These processors can perform the same functions, whereby you could have a very big execution. Like an example is those scenarios whereby systems are being used to perform complex mathematical functions. So since it is a complex mathematical function, it can be worked on because it could be heavy on one processor. It can be given to several processors to work on it. So think about it in those lines. Then we also have the characteristic of a distributed operating system, whereby there is this illusion of having a single main memory and a secondary memory space, but in real sense, it is multiple main memories and multiple secondary memories which are being viewed as one. So when we talk of distributed systems, now start thinking of the cloud architecture, where you are trying to access storage as a service from somewhere, you are trying to access process as a service from somewhere. So your machine doesn't have that kind of capacity, but you are able to borrow or to purchase some service somewhere, which appears like it is within your machine. And when I talk of cloud, think of an example like this cloud where we are posting our pictures. You're putting them, what is it called? Or the Google Drive. Google Drive, when you open it, you will see all your documents. Sindio? But those documents could be stored in different locations, but to you, they appear like one storage in the Google Drive. Also the Google Photos, or what are they called? Here kuweka picha inaitwaje? Who knows it? Does anybody know? In your mobile phones, maybe your mobile phone doesn't have enough memory, and you see, they ask you, do you want to store it in this? What is the name? Somebody with an idea?
Google
Any idea?
Photos.
Any idea? Yes, Google Photos. That is an example, and I know there are several others. I can't remember the names, but think of the Google Drive, the Google Photos. You know, they are able to store for you all this because you don't have enough storage within your device. They store for you somewhere, and you can be able to access them as if they are on your phone, as long as you have internet connection, but they could be somewhere in different storages. That is the illusion provided by distributed operating systems. So most of the modern operating systems appear in that distributed manner. Then there is also object-oriented design, whereby you can add modular extensions to a small kernel, whereby as much as your system is able to perform 1, 2, 3 functions, like we were just talking about, then you can customize your operating system without disrupting the system integrity. And this we will see with the Linux-based operating systems. Like for example, in Ubuntu or in Kali Linux, you are able to add other modular extensions to your operating system and it works fine. So examples of operating systems are like Windows 2000. These ones I will leave you to look at, whereby we are talking about the 32-bit microprocessor, and it provides the full multitasking in a single user environment, and it has client-server computing aspect. When we talk about client-server, we mean what? There is the aspect of a client requesting for services in the server. Then this is how it is organized. Then the layered structure, look at it, and if it has a challenge, let me know. When we are talking about the hardware abstraction layer, we are talking about it isolating the operating system from platform-specific hardware differences. That is why you can install Windows on any hardware platform, be it HP, Dell, I don't know which other manufacturer, and it works without any problem. So these ones, we shall be looking at them when we shall be doing the practicals in installing the operating systems. So that is what we mean by the Windows operating systems. Then we have the REDs, which are described there. Then we have the Unix operating system, which is the father of Linux, and it also has its own characteristics. So you can look at them, and we shall revisit this one when we will be doing the practicals. So that is basically how the two classes of operating systems normally work.